Okay, welcome back. So in the previous video, we were trying to prove Stirling's formula, and we were considering the sequence dn. And what we showed last time is that we got an upper bound for the forward difference for dn, and then we got an explicit series representation for the forward difference for dn. So in this video, we're going to show that dn actually converges to something, and we're going to show that its limit is positive, and that whatever the limit is equal to, that this expression is true. So this is going to get us pretty close to Stirling's formula, and in the last video, we're basically just going to find an explicit value for this expression here, and that will finish the proof. Okay. So what else can we say about the forward difference of dn? So it has a nice telescoping property, right? Meaning if I add, so I'm going to sum over k equals 1 to n minus 1. And here I'll assume that n is greater than or equal to 2, so that the telescoping can happen in the way that I want it to. And I'm going to add dk minus dk plus 1. And I want to note that this is a telescoping sum, because this is like, d1 minus d2, and then the next term would be d2 minus d3 plus ... And all of the terms in the middle kind of cancel. And so what this sum is actually equal to, if you cancel everything, is it's equal to d1 minus dn. And you can check that d1 is just equal to log 0 and then minus 3/2 times log 0 plus 1. So really this is the same as 1 minus dn, because d1 is 1. Great, but we also have a bound for these forward differences, right? So we know that we can bound this by k equals 1 to n minus 1, and then I'll have 1/3 1 over, and then I'll have 2k plus 1 squared minus 1, because I know that this bound holds for each of the forward differences. Great. But so now what is this other sum equal to? So this is equal to 1/3 sum k equals 1 to n minus 1. And if you simplify on the bottom, this is just 1 over 4k squared plus 4k. So if I pull out the 1/4, that's the same as 1/12. And then I would have the sum k equals 1 to n minus 1. And then I have 1 over k squared plus k, which is the same as k plus 1. So these are equal. Okay, but so now you can check that for a specific value of k, so for any of these specific values of k, that the summand here is equal to 1 over k minus 1 over k plus 1. So this is the same thing. And what that means is that this is another telescoping sum, right? Because the 1 over k plus 1 telescopes with the 1 over k as the value increases. So this is a telescoping sum, and it telescopes into 1 minus 1 over n. Cool. So what did we just show? Well, we showed that this sum, which was 1 minus dn, we showed that this is bounded above by 1/12, 1 minus 1 over n. And again, if you assume that n is at least 2, this is a positive number, and it is less than 1. So this is less than 1/12. And so now if I rearrange a little bit, I have 1 minus 1/12, which is 11/12, is less than dn, at least for n greater than or equal to 2. So, why is this important? Well, it doesn't really matter that I showed that this is bounded below by 11/12 specifically. It basically just matters that I showed that it's bounded below by something, right? And so now we want to recall again that we had this expression here for the forward difference dn minus dn plus 1. And this is a series that is strictly greater than 0 for all natural numbers n. And so together, these two facts imply that dn is bounded below by something, and dn minus dn plus 1 is positive, so dn is greater than dn plus 1. And so this actually means that dn is a monotonically decreasing sequence. So this part gives me that it's decreasing. And then this tells me that it's bounded below. So in particular, that tells me that the limit of dn as n goes to infinity does actually exist. And because all of the dn's are bounded below by something positive, it tells me that the limit is also positive. Great. So this was the first thing that we wanted to show. But now we can see that if we go back to our definition for dn, so dn was log n factorial minus n plus 1/2 log n plus n. So the limit of this we just showed is equal to some c, which is greater than 0. And if we raise e to the power of both sides of this expression, so meaning I'm going to do e to the power of this limit, I know that that's equal to e to the power of c. And then I can bring this limit down. So I have the limit as n goes to infinity of e to the log n factorial minus n plus 1/2 log n plus n. And I know that this is equal to e to the c. So we are almost done with what we wanted to prove for this video. Now we want to just simplify the inside of this expression. And we have e to the log n factorial, which is just n factorial. Okay, and then we are multiplying by, so from this part here we have e to the negative n plus 1/2 log n. And using log properties, that's the same as e to the log and then n to the power of negative n plus 1/2. So that just simplifies into n to the negative n plus 1/2. Great, and then finally we have e to the n. So this tells us that the limit of this expression, after we kind of simplify, is e to the c. And then all we have to do is just move this expression and this expression to the other side. And that tells us that the limit as n goes to infinity of n factorial is the limit as n goes to infinity of n to the now positive n plus 1/2 times e to the n. Oh, oops, sorry, this should have been e to the positive n. And so now this is e to the negative n times c. And I guess maybe you don't really need to do this last step. Yeah. I mean, I guess all you really need to know is that the limit as n goes to infinity of this expression, you can basically just divide by e to the c. So I have n plus 1/2 e to the n, e to the negative c. And I know that this limit is equal to 1. And this is the same as saying that n factorial is asymptotic to n to the n plus 1/2 e to the negative n e to the c. And this is the other thing that we were trying to show in this video. So that's it. So the only thing that's left to show is that this e to the c is equal to square root of 2 pi. And we will do that in the next video.